Welcome to week 2. We are now moving on from kind of the definitions of metallography and microstructure and lab safety into breaking down each of these steps for proper metallographic preparation. And so now we're going to start talking about sample selection, sample orientation, and some of the sectioning techniques. So the objective really is, how do you get from point A to point B? Looking at your image on the left are essentially cast iron journals that are used in a compressor for a vehicle. And, due to some flaws, they wanted to see what the material's microstructural was. So looking at the image on your right, which is an image of the microstructure taken at 100 magnification, you see what the structure is. And that was done through a comparison of, I think I had 36 total samples for that study. So how do we get from something that you physically hold in your hand to where you can get an image that you look at under the microscope to be able to relay results back to the client so they can look at either going back to the manufacturer, looking at design flaws or possible changes in their heat treatments? Well, for sample prep, first thing you need to do is understand that with your physical sample, they're going to be too large. So you're going to have to cut it down, then you're going to mount it. And if you follow the arrows, the top left image, that's your sample. And then when you section it, you mount it, so you move to the right, and you see it's encased in some type of mounting media. Then you polish the surface as you move down to the next image in the bottom right corner. And that's where you grind and polish the sample. And after attacking it with a chemical or etching it, the sample on the bottom left is going to be where you look under the light microscope and you reveal a grain structure. And that grain structure is what's going to tell you everything there is to know about this material. Well, 90% of the time. So the importance is not just the grind, polish, and etch step. It starts from when you first have to select your sample. Okay. And when you select that sample, now the next important step is, how do you section it? So after you choose the method in which you section your sample, you're going to clean the sample. All right, cleaning is a very big process. So if, the whole aspect of metallography and the preparation is very tedious, because everything results into something you have to clean after just about every step. Okay. So anyway, I normally ultrasonicate my samples between every metallographic step. So after I section a sample, it gets cleaned, and that's to ensure that you have a good bond with your mount. And then, of course, after each subsequent step in the metallographic process, I also ultrasonically clean. That just helps me remove any debris created from the previous steps. And then I get to the point of etching, in which after I etch, I still ultrasonically clean the sample just to get any remaining residue of the etchant off the samples, so that way I don't damage the microscope when I place the sample there. So the whole purpose, though, is to be, when you're following these steps, is to be careful, because you want to reveal the accurate microstructure. So how do you get from a big sample into a small sample? Well, this is where different types of sectioning techniques come in handy. For instance, case in point, majority of the work that's performed here at the lab I work at are pipe samples, and these guys come in 40-foot sections, 80-foot sections. something that is typically not going to fit into my lab. So I have to cut the area of interest out. And in doing so, the oxyacetylene torch or arc plasma cutter are the methods to go to just to get a panel out from a 40-foot section. Now I have a 2-foot section, much more easier to handle, something I can put on the bandsaw. So the problem with oxyacetylene or arc plasma is the fact that it generates a lot of heat in the sample. And generating heat into a sample is not good, because when you generate heat, you alter the microstructure. So once again, when it comes back to accuracy, you will not have that accuracy in determining whether or not that's the true microstructure. So in order to use this technique successfully, the general rule of thumb is to cut 12 inches in all directions from the point of interest that you're looking at. So that way the heat doesn't affect that specific area. So when I mentioned a 2-foot sample, if the area of interest is right in the middle, 12 inches on each side, gives me a 2-foot sample. Then now I can move to something that is easily controllable, like a bandsaw or hacksaw. Well, definitely not a hacksaw, otherwise I'll have arms like Popeye. But the bandsaw would be an easy way to now cut off and make my sample much, much smaller. An angle grinder can also be used. It also can generate a lot of heat, but not nearly as much as what you would expect from torch cutting. You're not melting metal, you're just getting it very hot in areas near and around what you're looking at. But we still recommend 8 to 12 inches from the area of interest that you're looking at. The bandsaw, you can essentially cut right through the area you're interested in. That's just because majority of the bandsaws come with some type of lubricant or cooling, and that obviously helps keep the sample from overheating or generating heat at all. So you're able to actually cut through areas of interest using a bandsaw. If you don't have a bandsaw, then some of the other options you have, and this is something that you will be working on in the labs, are the lubricant cooled abrasive cutoff wheels and or precision saws. So the lubricant abrasive cutoff wheel is very clean compared to a hacksaw or bandsaw cut. It's a super smooth surface, minimal amount of surface damage compared to the bandsaw. And so because it's quick, it's cool, it's clean, all you have to do is clean your sample after it comes out, and you're ready to mount the sample immediately after you're done. The precision saw is very similar to the lubricant cooled abrasive cutoff wheel, just on a super small scale. Precision is exactly what it's intended for. You can cut 2mm discs, something that is not obtainable using the larger abrasive cutoff wheel. Water jet sectioning. This is an important technique, especially if you're dealing with materials that you do not want to induce any type of thermal alterations to the microstructure. High temperature components, for instance, turbine blades would be one that this technique is very useful for. And the reason why is because when you're trying to characterize a material that has seen high temperature use, you do not want to generate further thermal damage, therefore altering and or changing the microstructure, which will then lead to misinterpretation. So water jet sectioning is very effective for not only cutting very large samples, but it does so without inducing any thermal alterations. And for those that are not familiar with water jet sectioning, all it is a blast or stream of water under very high pressure, and within this water, typically they use garnet, and which is a type of an alumina powder um, with sharp edges on them, and that under pressure with the stream of the water is enough to cut through very thick materials. The thickest material I've seen cut using this method has been 4-inch thick steel, and it does so with a very smooth surface. So very, very effective and very precise. It uses a computer program that you can tell it what to cut, and after it's all set up, then you can walk away from the machine until it's done. The next method for sectioning, wire EDM. This particular one here, you can cut very small, intricate features into the material. It does leave a slight recast or remelt layer on the surface. So during any type of metallographic preparation, you just have to make sure that you grind through enough of that to reveal the true microstructure, not the recast or remelted microstructure. So since we're using, bandsaws or abrasive cutoff wheels, when you're going to use a bandsaw, these can produce samples very quickly. And of course, they're going to have lubricants, so you don't have to worry about the material overheating and altering microstructures. And I typically use the bandsaw on materials that have low hardness. The reason why is because the blade that I have on the bandsaw, I do not want to go and spend a lot of money on very expensive blades for one-time use. I would rather do that on the abrasive lubricant-cooled wheel. So I typically cut softer materials on the bandsaw, and the only downfall, yes, you get a clean cut, but it's not, you still have a lot of mechanical damage on that edge, and that will definitely need to be ground through enough during the metallographic process. Then when you look at the abrasive cutoff wheels, this already provides you a smooth surface, a much smaller mechanical damage layer, and really the choice of the blade, the cutting fluids and or lubricants, and hardness of the material are going to play a large role on the quality of the cut that is performed. Okay, if you're cutting a very hard material with the wrong blade, then you can actually mechanically deform the material, creating a harder surface to cut. If you're using or lack of cutting fluids and lubricants, you overheat the sample, and then what ends up happening is you end up with these very large burrs, material smearing, and that will alter your microstructure. And then once again, the hardness of the material is going to play a role. So once again, if it's a hard material, you're using the wrong blade, that ends up being an issue. So you need to make sure that the choices between those 3 or 4 combinations are going to give you the optimal sectioning method you can just move right into metallography. Okay. Now there are 2 terms when it comes to discussing the blades themselves. Okay, and when you think of the term hard, you're thinking strong, tough. You're not going to have to worry about, the blade will last forever. And then soft must be used for soft materials, things like that. Well, in this case, it doesn't refer to the hardness of the abrasive particle. This is going to be how fast the blades break down. So a soft bonded blade refers to something that deteriorates quickly. So as you're using it, you can see that the blade is getting smaller and smaller when you use it. Okay. A hard bonded blade is going to be something that deteriorates far more slowly. And so you can use that blade over and over and over again, and it's not going to deteriorate as fast. So keeping those in mind, we have on this the blade selection. So for soft and non-ferrous materials, so your aluminums, titaniums, copper, you're going to use the hard silicon carbide blade. There's your hard bonded, okay? And hard meant it would last longer. It doesn't deteriorate quickly, okay? So you see in the hard and ferrous metals, so hard or stainless steel, quench and tempered, some of your tool steels, those materials you're going to be cutting with a soft bonded, so the one that wears away quickly. And then for ceramics, you have your diamond impregnated blades, and those are typically cut on the precision wheel for any type of ceramics. So going into soft, and the kind of the theory behind it is when you're cutting a soft material, okay, like aluminum, you're going to want to use that rubber bonded silicon carbide blade. And the purpose of the rubber bond is to hold the particles of silicon carbide in place. Since it's a soft material, you can use this blade over and over and over again. Okay. And the only thing you have to worry about in some instances is not to use a blade that you used for aluminum on and then go and try to cut steel or copper with it. Okay. Because some of these soft materials, one of the things it does is they can smear onto the blade itself. So the purpose of this, because of the fact that these are small, soft materials, as you're cutting with this rubber bonded blade and it's holding the silicon carbides in place, you have a fresh cutting surface all the time. The hard ferrous metals, the soft bonded blade, if you were to use a rubber bonded blade on a tool steel, something that has a very high hardness, then what you're going to end up doing is you're going to the particles themselves on the blade aren't going to hold long enough. You're not revealing a fresh cut surface or fresh particles to cut and abrade with each rotation. So the resin bonded blades allow that to happen, continuously freshening that cutting surface of the blade onto a hard material. So with that being said, you're going to want to use a resin bonded blade, soft bonded blade, and they wear away faster because with each rotation and in contact with the metal, you are essentially removing the old cutting surface, revealing a new fresh surface. So that's why they wear away the fastest. Hopefully that makes sense. For sample orientation, this is where things can start getting tricky, especially in writing reports. But when you're looking at a cylindrical specimen on the left, you're looking at two different orientations that can be described when you're trying to utilize descriptors on how you're going to position the sample. So if I'm looking at the cylindrical sample, I'm going to use my pencil here, and I'll use yellow. The axial orientation is going to be kind of described as the axis of the material. So it's going to be this guy right here. That's the orientation. Okay, this is axial. Now, when you want to talk about circumferential, well, that's going to be the opposite. That's going to be as if you were looking at it in this orientation. So if I were to take a blade and cut right along where that orange arrow is, that's going to be my circumferential orientation. Okay. Now, for the rectangular piece, I'll use a blue for this guy. Let's go with black. So on this one, I have axial. Okay. Well, when this sheet is produced, it is rolled in this orientation. So this would be my axial orientation. Okay. Then you have two transverse orientations. Transverse orientation number one, I'll mark this one in red, is going to be your short transverse. I'll just leave it as S. Your short transverse is going to be this little guy right here. That's the height. And then your long transverse, I'll use, let's do purple, in case anybody likes purple. Your long transverse is going to be this orientation here. Okay. And I'll just designate that as the letter L. So when you're discussing the orientation of the samples in a report, you'll say the cylindrical specimen, it had cracks in the axial orientation. So if we go back to our cylindrical sample, then that means I know that I will have cracks that are running this way, axially. Okay. If I have any flaws running in the circumferential orientation, then they would run this way. So that's how you would choose your terminology for when you're talking about sample orientation. And I'll have examples of this in class just to kind of run through and see how we can do this in the lab, to where we can identify orientation on the samples and become familiar, because this is going to play a role now when we move into mounting your samples. So we're designating what the orientation is here for particular shapes, and then from there we're going to move into talking about how to when you section it, what's the proper orientation for sectioning, and then what's the proper orientation for mounting. So for your assignments this week, we're looking at, if you haven't already registered for the EH&S Lab Safety course, please do so. And then this will be your first weekly summary to highlight anything useful from week 2 and how we could potentially help with your work, whether you're in industry and or doing research. Does it help to know about sample orientation, how to select your samples, and how to section your samples? I will have a week 2 quiz that'll be due on Sunday by midnight, and we will meet on Friday at 1:30, the way we did the last time on Blackboard Collaborate, where I'll be in the lab with a bunch of samples and we'll start to discuss orientations. So that'll be it for now. I will be on my Blackboard office hours today from 4 to 5. I look forward to seeing anybody there if you have any questions about today's short topic. And we'll see you then. Have a good day.